Welcome back, chemistry team, here for video number 5 in our Equilibrium series. Again, rather than be in our large lecture hall, we're in our mini lecture hall with our mini whiteboard. And I want to do it live like I would normally lecture. So I want you guys to have some familiarity, some comfort for what you've been used to in my goofy lectures with me just kind of rambling on and talking off the hip. I just wanted to keep it that way so you're comfortable. Now, more complicated problems, I'm probably going to do those on a PowerPoint. I just don't have enough board space behind me to do that and keep erasing. So those multi-page kind of problems, I'm going to put those in PowerPoint and go through and just hear my voice editing over that, guiding you through it. But that'll be in the future. We still got quite a few concepts of equilibrium to go through. So today, for this particular one, video 5, I just want to do a snapshot of where we're headed. So it's not technically in this introduction chapter to equilibrium for us, chapter 15. So I want to show you what's coming up and how to read and find these equilibrium constant values. So here's what we're going to be looking at, different types of Ks. So we looked at the generic K, right? So we could call everything just K if we wanted to, but we like to designate specific types of equilibrium with a subscript. We already looked at Kc versus Kp, right? So if we're using all of our species in our equilibrium expression or in the aqueous phase, we can use concentrations, typically molarity. If all of our species in our equilibrium expression are in the gas phase, we can use concentrations or partial pressures. So if we use partial pressures, we can use the Kp. And one of the earlier videos, I showed you how to interconvert between Kp and Kc. Now these are a lot more specific. So we're going to look at, I'll do one example of each. A for acid, weak acids, ionizing in water. B for weak bases, ionizing in water. W for water autoionizing, right? So really high-tech stuff here. SP is probably a little bit different, stands for solubility product constant. That's for solids, slightly soluble solids. That'll be in solution that are in equilibrium, right, with the solid dissolving and reforming. So we'll be able to calculate some amazing things later on. And then F is something completely new that I haven't taught you guys. It's for formation of complex ions. So in one of our later chapters, we're going to get into complex ion chemistry, which is really cool. There's some neat colors, but I'll do a slight introduction to it. All right, so let's start with, I'll do one board for each one. I'll erase it in between. So for Ka, we've already done the first 3. Let's do Ka. That will be for a weak acid that's ionizing in water. All right, so let's take any acid that's a weak acid. So for example, let's take nitrous acid, HNO2. And if you remember back from earlier chapters, that will actually donate a proton to water. So that's going to react with water in solution. And what that's going to do is donate its proton. That's what acids do over the water. So the water's acting as a base in this scenario. And so that is going to form the hydronium ion, the dreaded hydronium ion, H3O+. And then we're going to get the conjugate base of this weak acid. So I still today, after 30 years of doing this, cover up the H and look at the anion from that acid, which is the nitrite ion. So that'll be NO2-. All right. And of course, as we form more of these can actually react in a reverse direction where this hydronium is going to donate its H+ over to the nitrite ion and head back in the other direction until we achieve equilibrium and all the concentrations are constant. Of course, this is liquid, so we're not going to include that in the equilibrium expression because that's essentially constant, right? So let's write our equilibrium expression for this particular one. The one thing I love about acid and base equilibria, all the coefficients are 1. It makes it really easy to draw the equilibrium expression. So I'm going to write my K value, which will be the products. And I'm going to use, since they're in the aqueous phase, I'm going to use concentrations. That'll be raised to the power of 1, of course, times the other product, the nitrite ion, raised to the power of 1. And I'm going to divide that by the reactants. So the original nitrous acid, HNO2, raised to the power of 1. And I'm not going to include the water in there because it's a condensed phase. And I could leave that as K. I could even call that Kc generically, but specifically this is a weak acid ionizing in water. So a lot of people call that the acid ionization constant, the acid equilibrium constant, right? You'll see different things for that ionization constant. And we'll see the same thing in the next slide. for that, well, not slide, but board. And what you do is you look up in the appendix of your textbook, or for my class, if you look on Canvas, you can see these handouts. So I went through and typed all of these appendices out for you. So I'll give you an approach of this one. So this would be an example of an ionization Ka. They call it a Ka table, right? And typically they're done at 25 degrees Celsius. So what we do is just look down in alphabetical order, look for nitrous acid. You can see it right there. So nitrous acid is 7.2 times 10 to the minus 4. So we can write that up there. And this would be 7.2 times 10 to the minus 4. And then we can do some calculations with that. So if I know these and that, I can calculate this. If I know this and these, I can calculate that. There's a whole bunch of things we can do. And this is going to be the next chapter, right? But just I want to introduce to you. And look how small that value is, because K is less than 1. That means it's reactant dominant, which is true for weak acids, right? They don't drive a lot. If that was a strong acid, this would be a huge value, all right? So let me erase the board and do a KB for you, all right? So for KB, this would be a weak base ionizing in water. So let's take the prototypical weak base, which is ammonia, right? So we're going to be doing KBs. So let's take ammonia, NH3, dissolved in water. And of course, as you remember from prior chapters, weak bases are proton takers or acceptors. So if that ionizes in water, water will act as our acid in this scenario. So we're going to see that nitrogen with its lone pair on it taking the H plus from it, therefore acting as a base. Of course, it's a weak base. Strong bases, this would go to 100%. So in this scenario, this is going to lose an H plus, so we're going to get the hydroxide ion, right, which is your typical view from the Arrhenius theory that, bases form OH minus in water. This is going to pick up a hydrogen and a positive charge, so we're going to get NH4 plus, or the ammonium ion. So let's write the ammonium ion over here, NH4 plus, aqueous. And of course, as we produce more of the hydroxide ion and ammonium ion, they can react and go back the other way. So the ammonium ion can act as a weak acid in this scenario and donate its H plus to hydroxide to reform water. So we get a reversible reaction. Boom. Let's set up the equilibrium expression for this, just like we did with the other one. Let me grab a different color here. Dun, dun. So let's set up K. Let's take our products. Here's the hydroxide ion. Raised to the power of 1. We love acid and base equilibrium. Let's take the ammonium ion, raised to the power of 1. Let's take our reactants on the bottom. Let's take our ammonia, raised to the power of 1. And we don't include the water again because that's a condensed phase. So this will be, and we could say that's generically K or Kc, but specifically, that is a weak base. So sometimes you'll see this called the base equilibrium constant or base ionization constant right there, just like the Ka we did earlier. And we got tables for those, which I have typed out for you. Let's look up the value of Kb for this one. So let's grab a Kb, which is much smaller than the Ka table, right? So we got these organic amines. So this is a small table I put together, and we want to look up ammonia there. And you can download this on your phone, right? Or print out a hard copy from my website. So ammonia is easy. It's right up here on the top. And you can see it's 1.8 times 10 to the minus 5. Right on? So let's write 1.8 times 10 to the minus 5. And then I can use that constant to do equilibrium calculations. I think I had a cat just run in front of the screen. Welcome to my insane zoo of a house. Lots of fun. And I'm just going to make these videos as they roll, baby. I'm not going to edit these. All right? And again, that's a very small value, much smaller than 1, so it's reactant favored. We would expect that for a weak base. All right? So let's look at the next set with water. All right, for water, this is called an autoionization reaction. So let's put 2 water molecules. Even pure water will do this, right? So we're going to be looking at Kw in this scenario. So let's take a look at water with nothing else in it, just water by itself, right? Very, very weak, but this can actually autoionize by donating a proton to itself, another molecule of itself. So in that scenario, this water would pick up an H plus and turn into the hydronium ion. So we're going to get H3O plus. And then the other water lost an H plus, so it becomes OH minus. Right, so let's write our OA, our hydroxide ion over there. And of course, as we form more and more of these, this could react in a backwards direction, and we get a reversible reaction. And when those rates are equal to each other, we get equilibrium, and all the concentrations are constant. And this is going to be hugely important in some of the later chapters when we look at acid-base reactions, because if we're able to calculate the equilibrium concentration of the hydronium ion, we can get the pH from that. It's good stuff. All right, now let's set up our equilibrium expression. The hope is for this to become redundant for you, right? Setting up an equilibrium expression, just automatic. Give me the equilibrium equation, set up the equilibrium expression, look up the K value, boom, and now we can think, all right? So even if you're stuck on a test, don't know what you're doing, at least give me that. I can give you some partial credit, all right? So let's set up our K value. So let's take our products, right? So we got the hydronium ion there, raised to the power of 1, times the hydroxide ion raised to the power of 1. Let's divide that by our reactants. Now, water is a liquid that's condensed phase. I'm not going to include that or that, so I have no denominator. Oh my gosh, what am I going to do? Nothing, all right? We just leave it like that. This is a great one. And again, that's K, or we could say KC generically, but specifically, that's the water autoionization. So we're going to put a KW there. So you'll see that as the water autoionization constant. I will always give you that value. Autoionization constant. And that has a value. Depending, sig figs, depends who you talk to. I like to go 1.0 times 10 to the minus 14th. And that's roughly at room temperature, okay? Some people just go 1, call it exact. Some people go 1.00. Not going to be a big deal. Usually there's not many significant digits when you're looking at equilibrium constants. All right, so let's look at solid solubility next. All right, for solids dissolving, that can also achieve an equilibrium. This is just an introduction, so this is going to be for us chapter 18 later down the road. So we're going to look at KSP. We're almost done with these. All right, so let's say we've got some typical, what we would have considered an insoluble solid back in the earlier classes, but now we're going to call them slightly soluble. So let's just say, for example, we got cadmium hydroxide. If you look on your solubility chart, they would call that insoluble, but everything dissolves to some extent, even if it's just a few ions, all right? So what will happen is when that dissolves, water will come in, right? Because water's polar. You got that partial negative on the oxygen, partial positive on the hydrogen. They can rip these ions out. The higher the ion charges, the harder that is to do, right? But this will free up the cadmium 2 ion on this side. And then we're going to get 2 hydroxide ions as well. So we got to maintain that balance there. So that's our reaction. And as this dissolves and you form more and more of those cations and anions, the odds of them recombining to reform the solid increase. So this becomes a reversible reaction that will eventually achieve equilibrium. And then the concentrations of the cation and anions in solution are constant. So we'll be able to do things later on. If we know the equilibrium constant value for that, we can calculate the concentrations of these species, and a whole bunch of other things from that. Or if we know these, we could calculate the K value as well. So let's write the equilibrium expression for this. So we've got our K value. Let's do our products. So we've got the cadmium cation there, raised to the power of 1. We've got the anion, the hydroxide, but in this case, we've got a value of 2 there. So for some weird solids, you can get some really crazy exponents with some of these, which makes it a lot more fun. The acid and base ones, everything's to a power of 1. So that gets a little boring, but it's easy. We like that on exams, right? Now we could call that K, we could call that KC, but specifically, we're going to call that SP for solubility product constant. That's what that stands for. Solubility product constant. And of course, there's a table full of those, which, during some of my summer breaks, I decided to type those up for you. This one took forever, so make sure you download this from my website onto your phone, make some hard copies of that. And oh my goodness, I had to do everything, every single exponent, superscript and subscript myself. It was insanity. So we just look it up in alphabetical order. So we look up cadmium. I don't have my glasses on, so I can't see real well. I think cadmium hydroxide's right there. So it looks like that is a 2.5 times 10 to the minus 14th. If you look at it real close, cadmium hydroxide. 2.5 times 10 to the minus 14th. Let me get a pen and we can write that down. Now that's really small. And you'll see some teeny values for some of these solubility product constants, which means it's very heavily favored on this side over here. So you don't get hardly, so the smaller that value, the less soluble that solid is. The higher that value, the more soluble it is. But they tend to be really small numbers. So very simple to do. We'll do specific examples of this in later chapters. All right, guys, I'm going to skip the formation constants of complex ions because that gets a little crazy, and this particular video is getting a little long, and we'll get into some more juicy stuff in the next video. You guys are awesome.